Okay, here is the puzzle, the Tower of Hanoi. And yeah, this is how it works. Then you move these discs, and the point is to move the full tower of disk to another peg. But there is this rule that you cannot put something bigger on top of a smaller one. So yeah, you do something like this. Okay, so I moved 3, and of course now I have to continue and figure it out how to do this. Well, yeah, maybe I just undid something. So I actually don't know how to solve the puzzle just on my own, but you will see it's easy to write a piece of code. So well, let's just talk about it. If you have only one, well, hooray, that's easy to move anywhere. Okay, if you have 2 and you want to move these 2, let's say onto the middle peg, the middle rod, I move this one first and then move there. Oops, and now the problem is solved. Okay, if you have 3, it is slightly more complicated, but I think I just did that before. Okay, so well, I was not exactly sure where I wanted to move it. As I said, I'm not good at this, doing this, so I ended up moving the whole thing there. But okay, that's the idea. And there is a variant when you are not allowed to move just anywhere. So it's like in the basic version I can move this one there, but there is another version where it's sort of you can just move it to the next one. Okay, so well, you still can do it because well, this moving the smallest one there, it's actually consists of 2 moves. That's fine. Okay, so that's the constraint version. And yeah, it takes a bit of time to solve the puzzle for how many? Here I have 7. Okay, so that's how it looks like. Okay, so well, here's the recursive solution for the Tower of Hanoi. And what's difficult about recursive solutions that, you know, it's like we cannot do what I advocated before. It's just play in the REPL and it's just try to do in small pieces, try to have a piece of computation, then when you are happy with the examples, do the abstractions, identify the moving part and turn it into a function. Because for recursive functions, if you have to have the whole thing together in order to work, and it will not really work in pieces. So what we are trying to do here is just producing the moves for an optimal solution and just producing it as a string. Okay, so it's like, yeah, we are not going to literally move the disk around, we just sort of generate the solution for that. Okay, so let's call this function Hanoi, and we will have n, the number of disks, and we have the source, target, and the spare peg. Okay, so it's like, well, I mean, this could be anything. These will be just keywords. It's just sort of a thing to sort of talk about it. Okay, so it's the n is the number of disk we need to move. Source is where we need to move them, target where we want to put them in the spare, well, that's the extra one we can use when moving the disks. Okay, so base case, if the number of disks, well, if n, okay, well, let's just call it n, is 1, right? That's where it's like, it's a very simple case. I actually can show this, right? If that is the case, well, okay, let's say this is the source, this is the target, this is the spare. Well, we just move it from source to target. Okay, it's that easy. So I will just do a string. Let's have a space before that, and I just write the source, and let's have this arrow to the target. Okay, well, otherwise, well, let's just boot. Okay, well, it's like, it's not gonna work for the moment, but well, I can try the base case. Let's see how it works. So if I want to move just one, let's say I call them A, B, and C. So what I'm doing it is I'm calling that A, B, and C, just using keywords for that. So let's see, what do we get here? Well, okay, so it just says that, well, I have to move it from A to B. Sure, yeah, that's obvious. If I need to do 2, okay, well, I get boot because it's just not working. Well, fine. So obviously I have to work on this one. So this was the base case, but I just need to move one disk, and that was easy. But this is also not so difficult. Okay, it's actually, recursion is quite simple. It's just imagining the process and understanding it correctly. That's probably where it's a little bit of difficult. Okay, so let me see whether I can explain this. Okay, so it's like, if I need to move these 4, one might say that, okay, if I could move 3 together, well, to the spare, right, then I just move this one to the target, and if I could move 3 here, then I'm done. Okay, but it's like, you know, moving 3 together, that's not a legal move, it's not allowed. However, you know, that's a simple problem. The original problem is, oops, I got it. So the original problem is to move 4, but now if someone could do this to me to move 3, then it gets a lot easier. And this is exactly what happens in the code. So now we will have a big string, and it's like we call recursively, and we decrement. So we don't need to move n disk, but n minus 1. Okay, and if I can move from the source to the spare, and I can use the target as the spare, so this gets a bit confusing because it's like, okay, I call them source, target, and spare, and now it's sort of it's different. So maybe there is a better version of this, but yeah, hopefully that's not too confusing. So moving 3 to the spare, and I can use the target. Okay, and that's like, okay, this can be done. It's like, who cares how? It's like, but if someone can do for me n-1 moving, then I just have a very simple problem. Okay, I just have to well, again, it's like the same thing. I just move from source to target. Okay, that's where. Okay, where am I now? I move these three here, and I'm moving that there. Okay, that's the situation now. Well, I think it comes out the other way around for you, but that's fine. So now, what do I have to do? Well, I have to move 3 from this pair to the target, and I can of course use the original source as the spare. So that's Hanoi. Again, I just move 3, and now I'm moving from the spare to the target and using the source as the spare. Okay. So let's see whether this gives us a good solution for 2. Okay, how do you see that? Well, it's like, okay, let's call this one A, B, and C. So I have to move from A to C, and A to B, and C to B. Hooray! Okay, so that works fine. Let's see, can we do it with 3? Okay, we got the instructions. So let's try that. Well, it says A to B, A to C, B to C, A to B, C to A, C to B, and A to B. Okay, so that works fine. So now, can I do this for 7 disks? And yes, I can. Okay, well, I mean, I'm not going to do this in this video because this would take some time to follow, but you might want to check it for yourself. But the point is that once we have this recursive algorithm, how about 10? Yeah, sure. Why not? So, you know, it's surprisingly elegant, and it's just the same idea. At the base case, if we have a disk to move, or just a single disk to move, then it's easy. We just move it from source to target, and we don't even have to care about the spare one. Okay. If we need to do more than one, then, well, we just take one less and just, you know, ask this function to do it again. And we don't care about the details. But if we can move n-1 to the spare, then we just move the big one to the target, and then we move it back. So it is remarkably simple. However, of course, there is quite a process behind. But it's like, okay, this is like you're starting to see the power of recursion. This is a puzzle that can be quite puzzling for people if you want to do it, because, well, we don't think mechanistically, and if you make a mistake, then you tend to undo it, and it takes a long time. So it's quite challenging. But as you see, there is a sort of a mechanical solution, which just it's just long. But coding it is actually quite easy.